This is probably the most visually and auditory stunning version of our episode that we've ever done.
Absolutely, this has to be seen. This
Yeah,
is
yeah, yeah.
really,
Seriously,
really
like if you're
fantastic.
listening to this, you're missing a lot of the feel.
Welcome to Impact
Doing the
Quantum.
jitterbug. The universe dances, it's snug as a rug. Quantum podcast, turn it up fast. Candace and Frank blowing my mind at last. Quantum podcast.
Hello and welcome to Impact Quantum, the podcast where we explore the emerging industry of quantum computing. And you don't need to be a PhD, you just need to be a little bit curious. And with me on this journey is the most quantum curious person I know, Candace Gahuli. How's it going, Candace?
It's great. Thank you for asking. I'm really excited. We have something different for today.
Yes, and
Yeah,
very cool.
it's going to be very cool. We have a gentleman by the name of Wiktor Mazin. He's a PhD. He is a pioneer of quantum fractal art, and we're going to learn more about that today. So, hi, how are you? How are you doing today?
I'm good, thank you. Been looking forward to this. Thank you for having me here today. And how are you guys doing?
Doing well, doing well. We just got a foot of snow and down here in Baltimore, and we're not used to that like they are up in Montreal.
Yeah.
And my grandfather was from Montreal, so whenever we got snow, he'd be like, this is like a spring day. So, but with that in mind, I'm very excited to hear about this because I think art is one of those things that's uniquely human. You know, AI generated images notwithstanding, but that's a whole other rabbit hole. But I think it's not only uniquely human, but I also think it helps people process really weird abstract ideas, right? Whether we're talking about cave paintings where they show like, hey, look, this is how we hunt the animals, and I mean, this is something that's very much uniquely human, and up until 2022, I suppose, but we were the only ones that we knew of that used art, and art is one of those things that's universal across all cultures. And whether it's cave paintings in Lazoo or caves paintings or rock paintings, all the way up to modern art. And what's really exciting is that you've kind of taken this really weird abstract aspect of mathematics, which is not everyone's cup of tea, and you've made something beautiful out of it. I think that's cool because I think everyone can appreciate beauty. Obviously, what constitutes beauty is very subjective, but the fact that everyone can appreciate beauty, I think, is universal.
And if I can add to it, what I think also been missing for me at least, I've been in the quantum field for like 5 years. I'm going to explain that. Where are the visuals? Where's the beauty in quantum? I see a lot of papers, nice papers. It's not that, but how can you see quantum? You can't see that, right? So every person has their own idea or something, abstract. And I'm trying to make that a bit concrete. We haven't found some kind of a logic way of how to visualize that.
That's a great way to put it because I first saw the thing that made it click for me was I saw a vector graph where they were basically, and that's kind of, it was like a 2D block sphere, right? Block spheres were helpful too, but if you don't know the context, but like when I saw that, because I'm like, how could 0 plus 1 be something else, right? Because going back to kindergarten, 0 plus 1 is still 1. Like, what is that? And then the presenter was like, no, you're adding vectors. And I was like, oh, that makes a lot more sense, right? And then when you see a block sphere where it's like, wait, it's really more complicated than even just the 2D map. The 2D map was the first thing that got my head around it. And then when I saw the block sphere and like the 3D, and maybe it goes up to more dimensions than 3, for all we know, or for all I know anyway. You have the PhD.
I'm going to show the block sphere.
Yeah, I would love to see this because I'm fascinated by it. In the virtual green room, you did kind of, there's a preview of it, and I'm like, this is awesome because I remember when fractals. Not when they first come out. I don't know when they first came out, but I remember in the 90s, I was in university and they were like, no, this is mathematically generated art. And I'm like, that's crazy. You zoom in, it's the same thing. You zoom in again, it's the same thing. You zoom out infinitely, it's the same thing. It's a bit like a coastline, right? A coastline from space has this jagged kind of edges. And you zoom in, it's still jagged, and it's kind of the, I don't know, for me, like it was the mystery of nature almost.
Yeah, exactly. And that's why I think it connects good with quantum, where we are saying, right, we're working with the fundamentals of nature, with particles. We're working with
Right.
nature basically. So if you can connect that to some nature math, which I think fractal math is, then suddenly your things are coming together
Yes, that's a good
in
way
some
to
way.
poke at it. I'm excited. I've seen some
Yeah.
of
So
your work, so I want to share it with the audience. And if you're watching
so
us, if you're listening to us, not watching us, be sure to check out the YouTube link that we'll send.
yeah. So let me share the presentation, okay?
Please.
For sure.
Include the sound. Okay. Okay. So you hopefully see some nice images.
Yes.
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 So as I said, this is a personal project of mine, like independent of my work. But let me start by asking. So I alluded to this before, but the way I normally present this, then I say, imagine you could see quantum mechanics. I mean, imagine you could see quantum states. I'm going to explain that later. Come alive and art, so you can discover just how intricate and beautiful quantum phenomena can be. So I studied at the Technical University of Denmark like 30 years ago at the Department of Physics. I studied something called chaos theory. Perhaps you heard about the butterfly effect,
Yes.
shooting patterns and fractals. And then I was quite amazed that you could create these beautiful patterns with very simple recursive math. It was a very simple equation, and I'm going to show that. So if we fast forward a bit, then around 5 years ago, I started to upskill in quantum computing because I wanted to learn. So I became a Qiskit advocate, which means I know a little bit about quantum computing. I'm not super duper expert in all areas. I know a little bit, but I was very interested in how you can program a quantum computer. And then, one day I was upskilling, and suddenly I still can't remember exactly how, whether it was a dream or how it came to me, but suddenly it like hit me. Why hadn't anybody coupled these complex numbers, the complex amplitudes that you use in quantum mechanics and quantum computing, with the complex numbers you use to create fractals? And ever since I got that idea, I combined these two domains, and that's how I ended up with these, I think, amazing patterns that I'm real thrilled to share with you here today. So if it's okay, I'm going to just tell a little bit about the math connection between fractals and quantum computing, and show how these states, the quantum states, can be visualized, and also how they can be combined with music. And I'm also thrilled to present, I think, a first of its kind short film, the Jazz Quantum Fractal Film. But I'm going to show you guys this, and I'm very eager to hear what you think about it. So, first of all, what are fractals? And Frank, you already said that there are coastlines, and that's exactly right. But just to zoom out a little bit, some people know fractals, some people do not. But they're like complex geometric patterns that exhibit self-similarity at different scales. You have the coastlines, just as you said, Frank. You have the Romanesco broccoli, where each floret is like a miniature copy of the whole. You have the cactus here. They get a cactus with the fractal spiral patterns, and you have snowflakes. I really love snowflakes, where each snowflake, like intricate design, shows the fractal beauty at one of nature's smallest scales. And then when we zoom out to like the largest scale at all, then in galaxies you see these fractal spiral patterns. So also on the largest scales you see patterns that resemble fractals. So now we have some idea of where to find fractals. So let's have just a short look, just 2 slides here on the math part of it. So there are many different ways that you can create fractals, and I showed it here to the left. So one of the ways you can create fractals are something called the escape time fractals, or Julia set fractals. So with Julia set fractals, you iteratively or recursively update this famous function, and I call it famous after Mandelbrot. Perhaps some of you have heard about Mandelbrot. And this equation is really like this. From a math point of view, it's like a very simple equation. Z is equal to Z squared plus C. Nothing else, just this nice 3-term math equation. And C this last C, this is the part that I've been focusing on, and I'm gonna explain that. So, and it's known with this function that if this absolute value of z stays below 2 after a finite number of iterations, then we say that that point is within the Euler set, and then we color accordingly. I'm going to show you some examples of that. But just like hold on, that complex numbers are important when you are creating fractals. They are essential. Now, in quantum mechanics, on the other side, on the right side, in quantum computing, the quantum states, this is supposed to be some kind of a block sphere. I'm going to show you the real one afterwards. Then you represent quantum states with something called a state vector. And a state vector is made up of complex amplitudes which mathematically are complex numbers. So now we see that there can be a link, not that there is, but there can be a link between the complex numbers that you use in quantum mechanics and quantum computing and the complex numbers that you use to create fractals. And just I had the question sometimes, what are complex numbers? So they're they are numbers that consist like of two parts. There's a real part like this A, and there's an imaginary part, this BI, where I is this imaginary unit. And to simplify this a bit, so you use complex numbers in math when ordinary numbers are not enough. Signal analysis, quantum physics, and some fractal math. That's where you use complex numbers. So in that kind of special occasions, complex numbers really make sense.
So that formula there is A plus B times I, right?
That's how you normally would write a complex number. A real number A, B is a real number, but I is this imaginary unit.
Okay.
Exactly. And the Mandelbrot equation is this one, z equal to z squared plus c.
And C is a constant?
Yes, that's a constant,
Okay.
exactly.
Just checking.
You're right. Exactly.
The last time I did any kind of math like this academically was Kurt Cobain was still alive. So
Usually for me, it's been also a long time ago. So, I have to refresh and look some things up. So, but the thing that really got me that really not bothered me, but that intrigued me for some time was that this equation z equals z squared plus c, this c is just one complex number. It's a constant, this one constant. But normally when you deal with quantum computing and quantum mechanics, and when you use one qubit, just one qubit, the most simple quantum circuit just has one qubit, but one qubit, then you already need two complex numbers to describe a quantum state, or like a state vector with just one qubit. So I was wondering in the beginning, how can you then make sure you use all the quantum information instead of just compressing any number of complex numbers into just one constant? How can you do that differently? So it turns out, or if I zoom out just a second, so how many complex numbers at all can you take into account? It turns out, that we are looking at an exponential growth here. So if you have one qubit, you have two complex numbers. With two qubits, you have 4, 3, you have 8, 4 qubits, you have 16, and so forth. So you can see easily that's going to explode to a huge number. But way you can...
Is that one of the ways that you get all this like mathematical firepower from a quantum computer over a conventional system?
Yeah.
I'm sorry, I didn't mean to cut your flow, but I was just like, oh, okay.
Yeah.
Gotcha.
Right. But only up to a certain limit, then my computer simply breaks down. Because it's just the number, if you just have, 10, 15 qubits, the number gets so high that my memory, crashes. So only up to a certain limit, I can do this way. Okay? So one of the ways, there's something called Euler set mating. And there and I had to look the math up again. There's something called a rational function in math where you have a numerator and a denominator. So basically this equation you saw before, this Mandelbrot equation you saw here, basically I split up in two parts, with one of the complex numbers in the numerator and the other one in the denominator. As you hopefully see the first equation I have here. And what I very much like about this field, nobody has really looked a lot into this. So you can define the function any way you like, So like a huge canvas, they're just waiting to be explored. So I show here, here's an alternative way that you can make use of both complex numbers. Again, a rational function, but defined slightly differently. And as I mentioned before, with 2 qubits, you have 4 complex numbers, C0, C1, C2, C3. With 3 qubits, you have these 8 complex numbers going from C0 to C7. So one of the ways you can try to incorporate all this quantum information is by expanding this rational function. And this is one way that you can do it. And there are really many different ways. And each time you play around and you find a new way to express that math, you get a new visual expression of the fractal math. So this is really like, how do you define the fractal math that makes use of the of these complex numbers? So the block sphere, Frank. You hopefully see the block sphere to the left, right? So here you see the block sphere that you normally use to visualize like a 1 qubit state vector. And here you see 3 different fractal equations. And they are coming alive, in this case, from a superposition state. Hopefully, it's kind of clear that this state vector like travels along the equator here. So in this case, for each 6 degree, it could have been anything. But in this case, for each 6 degree, I take a snapshot. And I get the state vector. I get the 2 complex numbers for each 6 degree. And then I generate these 3 different fractal math animations. So in the first animation, I compress the 2 numbers, I divide them. So just have 1 complex number. So this is like kind of the Mandelbrot version, the very first animation you see here. In these 2 other animations, I make use of both complex numbers by using this rational function I showed you before, like this Julia set mating, one way of doing it and the other way of doing it. So hopefully it's clear that depending on the kind of math you use, you get different visual expressions. Does it make sense somehow?
Yeah, and it's interesting. What happens if you're just right now you're along the equator? Like, how does the visual change when you go in different directions?
So you will get a different kind of expression. I'm not sure it's going to be that different.
Mm-hmm.
But no, from all the time I played around, as long as you are off the axis and get more into some different parts of the space, you do get some different visual expressions. You do. But this is just here to illustrate that really depending on where you take the snapshots, you get a different expression. But yes, but you would get a different kind of fractals. So some of this initial quantum artwork here called the Qubit Carousel was actually exhibited in 2023 at the Microscope Gallery in New York. So here you see a slightly younger version of myself here in front of 3 noisy 7-qubit fractal pieces, because the criteria to exhibit at this exhibition was that the art was created using real quantum computers. So let me explain what I mean by that. So here in the middle image, this mostly yellow fractal, this has been created from I would call this an ideal or perfect fractal, because it has been created with an ideal or noiseless simulator, quantum simulator. No noise. This would be the result you would be if you ran exactly this quantum circuit. So it turns out that every time you take a circuit and you send it off to a quantum computer, and we know we are in the NISQ era, so quantum hardware is imperfect, it's noisy. So every time you get a result back, you get a new noisy and imperfect outcome back. So what I did here, I actually took 8 such images that I got back. And it depends on fractal math, but I use the same kind of fractal math. And hopefully you see that these images are variations of the ideal one you see in the middle. So from an artistic point of view, I really do believe that noise can be so much more beautiful than the ideal result that we are looking at here in the middle. So if it's okay, I become slightly philosophical, that make me like think, perhaps we shouldn't strive for perfection, as imperfection can be so much more beautiful. So all these small things, getting out from playing around with quantum computers, looking at the ideal result, and then what happens when you get noisy results back. All the beautiful variations that you can get back.
That's amazing.
Yeah. If you have any questions, comments, please.
Your comment about noise is interesting because there used to be a tool that was a plugin for Photoshop when I was in university called Kai's Power Tools Convolver. And it was basically you start with the ideal, and then like each one of them kind of would mutate in like different directions, and you would click it, and you would basically get, because you were strategically picking what type of a noise, you were able to get a very different and very, I think, much more improved version of your graphic that you were building by adding noise strategically. And I think that was interesting.
Yep. But also, I kind of like it from an artistic point of view, because all the focus of all hardware companies, right, is how can we get rid of the noise, right? So, and here and it makes sense because we want to trust the results. We want to have as precise and accurate results as we can. But from an art point of view, I like noise. So I use Python. I program this in Python and Qiskit and Penny Lane. I use different programming language, but primarily Python. So instead of using a default Python color map, to the left here, you see two fractal images with different colors. And to the left, so my wife one day asked me, why don't you let a quantum computer choose the color map? I was like, yeah, why not? Actually, that's a good idea. We all heard about these quantum computing random generated numbers. So why not let a quantum computer generate the numbers? So to the right, you see the same patterns, exactly the same patterns, but just with different quantum computer random generated color maps. The patterns aren't the same, but hopefully you see that the visual expressions are very different. So that's another dimension that you can add to art. Let a quantum computer, you can set up the code, sure, but then let the quantum computer choose what kind of colors to propose, and then you can choose between the colors. So it's kind of quantum human interaction. Okay. So in this piece here, I implemented an alternative version of an algorithm. That's called the Bernstein-Vasarani algorithm. That's not that important here, but what that enables is that you can enter any date or word, and then you can get a quantum state. And as soon as you have the quantum state, I love quantum states, because then you have the complex amplitudes, you have the complex numbers, and then I can generate the fractals. So I could take any words, I could take impact quantum, I could take your names, I could take my name, any name, and then see what kind of a quantum fractal you would get out of that. So here, last year we had the International Year of Quantum Science and Technology. So this is the kind of fractal that I entered these words, and then I got this fractal piece. And so I try to figure out, is there anything called quantum colors? So I look it up. So here I found something. I thought, with a little bit of imagination, it could look like a particle cloud. Okay, I mean, it's subjective, and I try to color here with the quantum colors, the 3 quark colors and 3 anticolors. So I love playing around, not just with the technical stuff, but how can I also somehow connect it with a small story? I'm gonna expand on that, especially on this one.
Oh, wow.
So this is one of my latest artworks. So here I entered the words, the four seasons. Where did I put that? Yeah, the 4 seasons. And I combined it with photos. So I live here in Denmark. So I've taken some photos during the different seasons in Denmark, and my wife and I, we love going to Sweden. So one of these photos, the last ones, is actually from a park in Sweden. And then I use AI to overlay. So what I think is what's important to me is, just not just everything is quantum, but how can we somehow tell the story, try to connect it to the world that we live in, because it easily gets so abstract when we talk about quantum. So I wanted to, as here, to explore different ways by combining these visuals, and I also like to add like a slightly poetic angle. This is really what I love about, letting this be a side project. I can try to express, creativity in a much different way than I can in my day job. And this is what I love about being, a technical person. But here, whatever comes to your mind, whatever you would like to express, you can do that in this creative way. So I tried here to combine these visuals, as I said here, with slightly poetic angle, exactly to relate the quantum principles to the seasonal cycles of nature, and trying this way to bridge the quantum world with the world we know it. So, if it's okay with you, I will just read the text on this
Yes, please.
slide.
Yeah.
So, I call it the haiku of continuity, quantum fractal symphony of the seasons. So, quantum fractals form spring to winter, states unfolding, fractals shape the year. So a year held in four quantum states, first blooming, then we have blazing, then we have blazing, right? And sorry, I just need to go back. Then we have softening, and then we have resting. And each season, that's like a fractal that's unfolding, each pattern a moment in the spiral of time. So across this cycle, quantum phenomena echo through the shifting forms. We have spring, rising in coherence, and summer that's bright with resonance, and autumn that's dissolving through entanglement fate, and winter that's settling into quiet decoherence. So a year shaped by the transitions of light and state unfolding in self-similar breath. Okay, so
That's cool.
try to
That's something everyone can relate to. The changing of the seasons. That's cool.
exactly, and that's what I try to convey, and also somehow connect it to the smallest, to the quantum nature, but also make it more tangible, something that we can see and relate to. So now this 5-qubit fractal, I'm very fond of. My wife and I are very fond of this one because, in my view, it looks hopefully both like a yin and yang symbol, like this wave in the middle, but also the bird with a little bit of imagination. Perhaps you see the bird's head here, right? The eyes, some feathers, the mouth up here. So I call this piece the quantum bird in the dance of yin and yang, bridging opposites in balance. And allow me here to again read the caption from my Instagram post here. So, in the infinite space of the quantum realm, a bird takes flight, navigating a path shaped by the entanglement of unseen forces. And encircled by yin and yang's eternal dance, it bridges the dualities and the interconnectedness of opposites. Light and dark, chaos and order, known and unknown. And the bird emerges as a symbol of unity, reminding us that even in contrast, there's a balance. Through quantum entanglement and cosmic balance, it finds its way home. The one funny thing about this is I live in Europe, and I read some time ago that there's something, there's some birds can navigate based on quantum principles. I know you had an earlier podcast episode about quantum biology. So there's the European robin is said to navigate using quantum entanglement in its eye by sensing the Earth's magnetic field. You use that when it migrates. So this is also kind of not slowly, but whenever there are opportunities, they're trying to connect again what happens in the quantum world with a slightly philosophical angle, but also to nature again, to nature as we know it. So I like this connecting things from sitting something, on my computer, seeing what happens when I get back, from the quantum technology I'm using, and then relating it again out to what happens in the wider world. So, yeah, it's like a whole journey, if that makes sense in some way.
That's amazing.
Right. It's fantastic. I'm really enjoying listening to your explanation as to why we're seeing it, how we're seeing it. I please continue. I think it's fantastic.
So I also turn my attention to, fractal animations because, as you said, Frank, fractals are known for that you can zoom in or out and you see the same patterns. They're repeating. So here I want to show you like what I call like a short journey. I call it into the mind of a quantum computer from this fractal art perspective. And why do I call it that? I call it that because it's based on a 7-qubit quantum circuit. So 7-qubit, if we translate that to the complex numbers, that's 128 complex numbers I use in this kind of math. But this quantum circuit has been run on real quantum hardware. So it's not a simulated real quantum hardware. So I'm going to play and let's see how well it goes through here in this recording. But I'm going to play this recording and you will see this fractal zoom. So we're going to zoom into this mind of a quantum computer, into this fractal. And I call this work like quantum hurricane thoughts. So let me show you this video.
That was cool.
Yes,
What
it
what
was fantastic.
what impressed me is like you had the sense of volume, like you were traveling
Mhm.
through something.
Through the image.
Yeah.
Thank you. Yes. Yeah. So, and it's really, again, this post-processing. I have this fractal, so how can I do it what can I do to make it more alive? So it's not just still images. And I think this is one of the ways where you also make use of the unique properties that fractals have that you can keep zooming in. So, I also want to show you this one. So I also started to look at 3D animations. And here I want to show like two short 3D videos, which I call like sensory journeys into quantum fractal universes. And I would encourage you to pay attention to these fine details because the fractals fine details become even more clear when you look at them in 3D. So let's have a look at this piece or these two short pieces that I call echoes of the quantum, a slow journey into the fractal landscape. So let me play this.
Oh, that's some hippie trippy stuff. That's very cool.
That was very cool. The second animation with the flower, it looked like a flower, and
Yeah,
like
yeah, that's what I thought.
it had a very, very real, organic feel to it.
Mm,
That was cool.
Thank you. That was the intention. Yeah.
yeah, that was fantastic.
So thank you. So now I've also been wondering, whether can these quantum fractals can they be used to to capture the attention of people who do not have a quantum physics background, I don't know anything about quantum computing, and start to get them interested, just to start to get them curious about certain topics, about certain quantum topics. So I put together this animation recently, and let me show you this video about coherence. Right, so coherence is when you have a quantum state, and when the quantum states are coherent, then you can do all kind of calculations why they are coherent. But due to different kind of environmental noise or errors, they can quickly decohere, and then you lose the ability to make calculations in that time. So here I try to visualize the coherence using three different fractals. And instead of always using entanglement like between two particles, I thought, okay, let's expand this a bit into three particles. So let me show you this piece here on coherence.
That was interesting.
Mm-hmm.
That was cool. I think this also can help visualize kind of like some of the weird things that are going on in quantum physics.
Yes, right? Because how do you even try to explain stuff like that, right?
Right.
I
And
know there are many arts.
especially if you're a visual learner, right? Like if you're a
Right.
visual
Yes,
learner, like this stuff is hard to get your head around because it's so
Mm-hmm.
counterintuitive to how we
yes,
experience everyday physics, like everyday reality. So no,
yeah,
that's cool.
I agree. I wish when I was studying at the university back then, we only had the books, right? Big books, a lot of text, almost no visuals, a lot of formula. It was tough, right? It was pretty tough if you guys remember that time. If there had been visual learning, much more YouTube back then, or different ways of learning some of the hard stuff, I think that could be for some of us, it would have been much more easy to grasp the concepts.
Yeah, there was a series of mathematical lectures that was I think it was a guy at Stanford. This was on PBS in like the 80s. And accompanying his lectures about these very weird, very, I wouldn't say abstract, but they were basically Maxwell's formula was the one that I remember the most, where he kind of shows the lines of force and all that, and very rudimentary computer graphics, for the time, but cutting edge at the time, right? But um, it helped me understand it, right? And I remember, and I still think back to those crazy probably done on Amiga graphics or something like that. But
Mhm.
no, you're right. Like it helps you get your head around things. That's interesting because the visual cortex is there. You might as well
Mhm.
use it for learning, right? Like,
Yeah, exactly.
I
Yeah.
just feel that, with the representation that you're showing, you've added like an emotional and an aesthetic kind of resonance to something that could really just be seen as engineering. When did you start thinking about the emotional and the aesthetic resonance of these quantum equations?
That's a good question, Candice. I think when I got the idea that I suddenly, not suddenly, but then, that I could visualize these quantum states using fractals, then suddenly, it like became even more apparent to me, how long time I've been looking too much at these books, as I said in the past. So it's really missing the visual component. And also, instead of everything having to be scientifically correct in papers, all that, I was really missing to express the creative side. So I was kind of, how can I do this differently? How can this appeal I'm trying to imagine how it could appeal, to somebody who's not in the field. How can I try to make these very um, theoretical concepts something a bit more tangible? So, um, besides my academic educations, I also have an education as a psychotherapist. So I do like to, how can you connect this to people in a different way? Because I think that can make such a much more powerful connection instead of just seeing some formulas or some papers. So I'm trying to bring different parts of my past into play because I think that creates something unique that hopefully some people can relate to.
Interesting. I think that's an interesting, like, kind of cross discipline, because one of the
Yeah.
things that, you know, Candace kind of said it, like it looked very hippy dippy trippy, right? Like paraphrasing, right? There's a psychedelic feel to this,
Hmm.
Yes.
with fractals in general. Like, and what does that say
Yes.
about our systems of perception? Or is it our systems of perception, or is it something fundamental in the universe? Because you have a lot of these things, popping up, whether they're mandalas in the Eastern tradition, whether it's, fractals in kind of modern Western math, or, you mentioned yin and yang, like these things, common themes tend to pop up. And I'm a believer, like, if not everyone's going to agree on everything, but if you have people who don't agree on everything, agree on a handful of things, that says something very
Yeah,
true and fundamental.
I agree. Yeah. So, so I very much like when you combine art forms. So it turns out also that you can take any sound or any piece of music and you can transform this, let's call it classical sound data. You can transform that into a quantum state using something called the quantum Fourier transform, signal analysis, quantum Fourier transform. So you can take this piece of normal music or sound into a quantum state, and then as you see, when you have a quantum state, I like that a lot because then I can turn it into fractals. So one of our good friends here in Denmark is called Christina Dahl, and she's like a professional jazz musician. She has won several prizes in Denmark, in Germany, and in Norway. So together with a colleague, we created this prototype film, and it features these quantum fractals that are generated based on segments of one of Christina's tracks called Souls of the Wind. And then it's combined with some AI generated images. So there's the details. You can read about the details in this article. But I want to show you like 2 minutes of what I believe is like the world's first jazz quantum fractal film. If it's okay with you, I'm just going to play like 2 minutes of this jazz
Oh,
quantum
sure. Yeah,
fractal
no, I'd
film.
love to see this, because that was my next question. How does this relate to sound, right? Because there's also auditory learners, but
Hmm.
also too,
Yeah.
like there's a lot of harmonics could be involved in here. So,
So be prepared for some Nordic jazz.
okay.
2 minutes. Okay.
That's cool.
You know, and by using music and using these visualizations, again, you are really substantially making something understandable using like all the senses. I'm just totally blown away.
Thank you. I really hope that many other people will also get into this so we can show different aspects of quantum, right? More the creative sides, the visual, the auditory. So I think there's a room for a lot more going on in this field.
Wow. That
So
is cool.
so last summer, then I presented my artwork at United Nations Quantum for Good Summit in Geneva, Switzerland, together with McKenna McGrew, and she's a quantum information scientist and quantum musician. So together we formed this band that we called Echoes from the Quantum, and we showcased quantum fractals and quantum music based on the same quantum states. So she composes music based on quantum states, and I create the fractals based on the same quantum states. So I'm just going to play here like 4 sections of this quantum music, around 30 seconds each. And for each section, then you will see a quantum fractal with some text again, where I again try to relate what goes on, or try to describe what goes on in the quantum world from an artistic point of view.
See, first I was really excited by the Huskies and
Yeah.
the sound that they made. I thought that was really, really exciting. But then you just showed us one. What was the last one that you showed us? Oh yeah, the living cell, the living like
Nice.
and the complexity of the quantum cell. Oh my
Yes.
God, that one blew me away.
Yeah, same here. And I was like, based on one qubit, and I was like, I wonder how we would hear that. And then when you get to the ones that are multiples, like, oh, I hear it now. I can't explain it. I can't explain it in words, but I'm like, I heard it. You can hear the different nodes, for lack of a better term. You can almost
So
hear
on
them.
this, so on the sound, I'm not a sound expert, but McKenna, she's really a sound expert, so she can explain this much better than I do. But I just want to say that this quantum cell, my wife and I got so fond of this one that we actually printed it out and we have it hanging on the wall like in a
Nice.
like a what do you call it, like a gallery print, like
Nice.
80 times 80 centimeters. It's really astonishing to look at.
Nice. Nice.
So so
This is
just
cool. This is probably the most visually and auditory stunning version of our episode that we've ever done.
Absolutely, this has to be seen.
Yeah,
This is
yeah, yeah.
really,
Seriously,
really
like if you're
fantastic.
listening to this, you're missing a lot of the feel. Plus, you're
I'll
not
go
seeing
to
my
the YouTube, right?
funky glasses.
I'll
Go
go to the
east.
So,
YouTube, right,
Yeah.
and look at it afterwards, right? So, but also I just have a few more slides, two more slides. So what McKenna and I also did, we look into complexity in quantum art. So that means that we're going from simple art, and by simple art, I mean this is based on quantum circuits that are easy to simulate on a classical computer, on a normal computer, to the more complex art, which means art that is based on quantum circuits, where you have different gates in them that make it more difficult to simulate classically. Without going into too many technical details, it is something to do with Clifford gates and non-Clifford gates. But let's not go into these technical details right now. But what we showed in an article where I can provide the link, of course, is that the artistic complexity can be measured by something called the Shannon entropy, right? Which is a measure of the amount of complexity and unpredictability you have in a system. And we could measure that the Shannon entropy is notably higher in the more complex art compared to the more simple art, both with the visuals, but also with the audio. So if you have a look here at these three fractals here, um, you have the same fractal math in all the columns from three different ways of making these fractals. In the top row, you see these nice symmetric ordered fractals, as we know them, very symmetric, very symmetrical. And this is based on the simple classical systems what we can do on a normal computer easily. But then when we get into the more complex math, you start to see, these more complex circuits, sorry, then you see how the math or how the fractal images also changes. And it's really a matter of preference whether you like the more ordered one or the more distorted, the more irregular ones. So I'm just curious here, are there any or which of these do you like
I kind of
like
like the
more?
upper middle one just because it has that pop art feel. I
mm-hmm,
don't know. I also like the lower right one.
Yeah.
mm-hmm.
And imagine this is just one set of colors. Then imagine you can add all kind of different color maps to it.
Yeah. So
You
you
can
mentioned that
really,
these are simulated. Have you tried to generate these on real quantum hardware?
so these ones are simulated uh, due to the time that we had to do this. But I could
Okay.
also had used the hardware. You're right. But
No,
then
like
I
how
would expect
would you get a different result? Would it be like a slightly different result or
yeah. So I would expect it because every time you run a hardware, you get this noisy result back, right? As
oh
we're in
yeah,
this
yeah.
era. So I would expect the result perhaps to become even more distorted. But how much each one gives you a new noisy result back. But I would expect it to become, I don't know if you could tell the difference between running the top one on a quantum computer and getting the results back versus the lower row, where you
Right.
already use complex circuits. But
Does
it could be
one
interesting.
type of I'm sorry. Does one type of quantum computer generate a different result? So like would an annealing circuit generate something different than say photonic or trapped ion? And Candace, I know I'm leaving out like two more other types. Like does the type of hardware you're running it on change the visual, or because these are base quantum phenomena, it shouldn't matter?
That's a very good question, Frank. I really look forward to getting access to different kind of hardware so I can test it out
Right.
and see like how big is the difference on different hardware versus the ideal one, right? How different are we from the ideal on different hardware? Do they make different visuals? That could be a great thing to look into. Hadn't had that
Wow.
opportunity yet, but definitely worth exploring.
Well, hopefully somebody in our audience can make that happen for you. So.
Yeah.
Right.
So, so the final piece I want to show today is called Infinity, as you see here, and this I've done in collaboration with a British contemporary artist, Michelle Jaffe Pierce, who's like a I would call traditional painter, but that's not. But she paints, right? So, and we have created several pieces of art inspired by each other. So to the left you see her painting, called Infinity. And here to the right, you see my quantum fractal art version of that one. And the reason why I want to close with this one is that I got so lucky that last year in Nature, the
Nice.
science journal Nature, they discovered my quantum fractal piece, right? And they featured it in a Nature review article that was commemorating the 100 years anniversary of quantum mechanics.
That's fantastic.
So that was kind of cool, just sitting and playing around, and suddenly, perhaps this can capture some of the complexity in some visual, abstract way, dealing with quantum computers. So, so I just want to say thank you, for joining me and for having me here. So hopefully you have an idea about what quantum fractal art is, and also you have some idea at least that quantum states can also be visualized as these
That's
intricate
very
and
cool.
beautiful patterns, and that it can all be combined with music also.
And for those who are not watching this, it's that was a QR code for your Instagram, which we'll make sure we have in the show notes because your Instagram
Yes.
is very fascinating.
Yeah, it's good.
Very cool stuff. Want to be respectful of your time. Plus, I do have kids home from school, and I can hear them decohering from here.
You have your own
and
visualization. I love
I
it.
got my own visualization there. Yeah, I
Right.
hear. I'm in the basement, and the playroom is upstairs, and I slowly hear the chaos going from like this noise level to like, yeah, there's a
Yep.
lot of quantum noise happening upstairs. But thank you very much. This has been probably the most fascinating, and we have a lot of fascinating guests, right? I'm not throwing shade at any of our previous guests, Candace.
No, I
But
know, but
wow,
this was
this
really
one,
cool. This was
yeah,
just
this one was
different.
very different and very cool.
Yeah.
And I appreciate what you're doing because I think you're doing, the Lord's work. You know what I mean? Like you're bringing, a lot of people think of art and science as two very different realms, but
Yes.
and then they are, but there's a
Yeah,
significant overlap too.
exactly. Well, I want to thank you again for allowing me time for this, because I know this was a different topic. I've
Yeah,
been
yeah.
to all the podcasts, so I was curious at all. Would you be open to this kind of art
Oh,
science?
absolutely.
Oh,
This
for
is
So,
sure.
this is
so thanks a
amazing
lot for having me
stuff.
here.
Yeah, no problem. And I know Candace does a lot of work with neurodiversity and things like that,
Yeah,
and has experience in that space. And I would suspect that there's, I don't, I mean, I just see an overlap there too, right? In terms of how different people learn, different learning styles and things like
yes,
that. I think there's an
exactly,
enormous, there are a lot of directions this could go.
Yeah,
exactly.
absolutely.
Awesome.
Well, thank you
Okay.
again so much for your time. And we'll
Well,
connect everyone to your Instagram.
thank you. Thanks a
Yeah,
lot.
awesome. Thanks for having us, and we'll play the outro music.
Quantum podcast, turn it up fast. Candace and Frank blowing my mind at last. Quantum podcast, they're breaking the mold. Science and sky beats, it's bold and it's gold. The multiverse is skanking in time. Black holes are wailing in a horn line so fine. From Planck scales to planets, they're connecting the dots. Candace and Frank, they're the cosmic hot shot. Quantum podcast, turn it up fast. Candace and Frank blowing my mind at last. Quantum podcast, they're breaking the mold. Science and sky beats, it's bold and it's gold.